Okay, the last section we're going to cover, 2.8, deals with tangent lines. In fact, our learning target just for today is I can use a tangent line to approximate functions. What I have highlighted here is the main idea. It's that the tangent line will stay close to the graph near the point of tangency. So take a look at this picture down below. In green, I've highlighted that. Here's some function. And there is some point, we could call it point P, which would have an x value. We could call it x naught. It would have a y value, of course. We could call it f of x naught. By the way, this is so important to even do this. The point of tangency, it's not a bad thing to write it down. The point of tangency is a point. It's your x naught, and then my y value, it's just going to be written this way, f of x naught. That's a good starting place. We're calling it point P in this picture. But imagine that we draw in that tangent line, and that's in red here. So you've got this red tangent line. Another point on the tangent line might be point Q over here. And just this picture right here has so much information chock full in this little diagram. Look, yeah, there is this x value that we're starting with, but let's just say we move over just a little bit. Let's just say we move over delta x. So we start with x naught, but we add delta x to that. So we have x naught plus delta x. Right now, we could talk about a point on that curve in green. We certainly could. That would be the true function value at x plus delta x. But we could also say, wow, right above that would be a point Q on the tangent line. And that would be pretty close to that y value. So that's what's going to drive this whole section today. A tangent line. You've been writing equations of tangent lines for a very long time now. If you think about it, you've probably been doing that for over a month. I think you can think back, reflect on it, and say, why have we been doing that? So what? We're writing tangent line equations. Why are we doing that? We do that because we can get approximations from them. And sometimes, in the context of a science lab, you might not know what your true function really looks like. You might have to resort to approximations to get a good idea as to what's occurring. So, right now, I think stating the obvious, we'd look at this picture, we'd say, well, my goodness, why not just work with the green function? Why even get an approximation? Sometimes we don't have that luxury. But look, we could have a delta x, we could have delta y would be the change in y from the point of tangency to this other point on the green curve. Look, I have delta L. L is going to be used as a line, L for line, tangent line. So we could talk about the true change in y on the curve. That's delta y. That's your two y values, y2 minus y1 being subtracted. But you could also talk about the change in y on the tangent line. That's delta L. And we'll talk more about that even in our second day here. Delta y over delta x is pretty close. That's your change in y over change in x. It's pretty close to f prime of x naught if delta x is very small. Okay, if delta x is very, very small. So let's take a look. Like I said, L of x is representing a line function. It's the tangent line function. And we could see that the change in L, the change that we see in the y values on the tangent line, are pretty close to the change in y that we see on the actual curve. And it's important to note that this delta L, the change in y on the tangent line, is not always going to be bigger than the true change of y values on the curve. But here's where we're going really for the big idea today. We're going to write the equation of a tangent line like you've been doing for the last month. But we're just going to go one step further. We're now going to use it to get some information. So in calculus, without a doubt, point slope is used extensively. It is the #1 method to write the equation of a line. And we just want to continue to reinforce that. And of course, if you need a point, the obvious need that we're going to have is to have a point of tangency. And in general, we'll have a beginning x value. We can call that x naught. And then we'll have the corresponding y value. That's f of x naught. So this would occur on our actual curve. But as you're looking at this picture, again in green, you can see what's happening right here. We've got x naught, and then we'll have a second x value sliding over just delta x. You can see that our delta y here is, the true change in y on the curve. Here's a red dot that we have that's a y value on the tangent line. I guess I just want to drive home that this right here is delta L. Delta L can be smaller than delta Y itself. That's what we just saw a moment ago. But my goodness, if you're going to write the equation of a line, you need slope. And guess what we've been using for slope of a tangent line? We've been studying this for months now. The derivative. It's the derivative of your function at that x value of tangency. And that's what we're going to see. So, just driving this home and writing this out, just so you can see where it's coming from exactly. You can say, well, here's my point slope form of a line. And you could say, well, what about your point of tangency? Well, you'd have y minus f of x naught. Here's your m. And here's x minus x naught. But the m we just talked about a second ago is really the derivative. So that's your f prime of x naught. And wow, right now, guys, one little thing. How about we move that f of x naught over? We add it to the other side. And you know where we're going with this. We've got this equation of a line where we have y all by itself. But like I said, the y is really going to be called L of x. And this is the equation of a tangent line. And we can use it to get approximations. Only one problem today, and then we're going to be through. Okay? Yeah. This right here. One second. So let's real quickly take a look at the one and only problem that we're going to be looking at today. Example 1. We've got a function, and I'm changing this. We're going to change this to write a linear approximation, estimate cosine of 62 degrees. First of all, we need f of x. F of x is the function at hand. I hope it's pretty obvious what function we're dealing with in this problem. Guess what f of x would have to be? Cosine of x. By the way, here's the other thing that we really need to be aware of. We need to have radians. Now, if I'm estimating 62 degrees plugged in for cosine, hopefully there is a point of tangency that's pretty close to the 62 degrees. What angle do you know on the unit circle that's super close to 62 degrees? 60 degrees. So tell you what, we're really going to say, you know what? I've got 60 degrees. And what is the cosine of 60 degrees? Cosine of 60 is 1/2. Now, like I said, you want to have this in terms of radians. You're going to have pi over 3, comma, 1/2. By the way, let's go ahead and even convert 62 degrees into radians. Hopefully you remember the pattern for that. What's the conversion factor? We'd multiply by pi over 180. And right now you'd look at that, you'd say, well, my gosh, I guess we could divide out a 2 perhaps. And if we did, we'd get 31. Divide out a 2 here, you'd get 90. You'd get 31 pi all over 90 radians. So this is what we'd like to estimate. We'd like to say plug in this 62 degrees as a radian, and let's see what we get. Now here's where we're going to have to go. We're going to use the equation of a tangent line. By the way, we're almost there. We're almost done, if you can believe it. Because I'm going to have y minus y1 equals m times x minus x1. And I guess what I really want to point out to you is that you already have x1 and y1. That's your point of tangency. Wow. We need the slope. We need to get the slope. How do you get that? Take the derivative. F prime of x. What's the derivative of cosine? Negative sine of x. But guess what I'm going to plug in? I'm going to plug in pi over 3. I'm working out my tangent line slope at the point of tangency. What is the sine of pi over 3? Radical 3 over 2. Don't forget there's a negative. So that's your tangent line slope. So I'm going to use my slope. I'm going to use my x and y. Right now, I hope this just seems like an ordinary problem. Many times you've written the equation of a tangent line. We're going to do it even right now. Here's your y1. You've got negative root 3 over 2. And then we'll say x minus pi over 3. Usually kids look at that and they'll say, okay. So now what? Guys, tell you what, you could add a 1/2 here if you'd like. And I guess what I really want to point out to you is that y right there is your L of x. That's your tangent line function, so to speak. Guess what we're going to plug in now? We're going to plug something into that. The estimate. We're going to say, you know what? We're supposed to figure out what's going on at 62 degrees. We're trying to figure that out. And you know what? That right there is our estimate. We're going to plug that in. And we're going to see what we get. So we get y is equal to negative root 3 over 2. Here's 31 pi over 90 minus pi over 3 plus 1/2. Let's get our calculator out. And let's see where we're going with this. I'm going to say negative. If you want to, you could get this up here and just type in the square root of 3 all over 2. You could make it look real nice. And again, you can say alpha y equals, get another fraction in there and go 31 pi. Down below, we'll say 90. Then we'll say minus, hey, we could get one more fraction up there, my word. Pi over 3. And then say plus 1/2. Hey, if you want to make it look especially, just like we just wrote out, you don't have to do the 1/2. You could do 0.5. You could say, hey, would you look at that? We're getting about 0.469 or about 0.470. So L of this thing right here is about 0.470. About 0.470. Look, change your mode back to degrees. And let's just see, what's the cosine of 62